For a manager, the probability of a future event presents a level of knowledge. The manager could know with certainty that the event will occur, for example, a legal contract exists. Or the manager may have no idea if the event will occur, for example, the event could occur or not occur as part of a new business opportunity. In most business situations, we cannot be certain about the occurrence of a future event, but if the probability of the event is known, then we have a better chance of making the best possible decision, compared to having no idea about the likely occurrence of the event. Business decisions and policies are often based on an implicit or assumed set of probabilities. To help you develop a clear and rigorous understanding of probability, we will first develop definitions and concepts that provide a structure for defining probabilities. These definitions and concepts, such as sample space, outcomes, and events, are the basic building blocks for defining and computing probabilities. Probability begins with the concept of a random experiment that can have two or more outcomes, but we do not know which will occur next. A random experiment is a process leading to two or more possible outcomes, without knowing exactly which outcome will occur. For example, a coin is tossed and the outcome is either a head or a tail. A customer enters a store and either purchases a shirt or does not. In each of the random experiments listed, we can specify the possible outcomes, defined as basic outcomes. We do not know in advance which outcome will occur. The possible outcomes from a random experiment are called the basic outcomes, and the set of all basic outcomes is called the sample space. We use the symbol S to denote the sample space. An investor follows the Dow Jones Industrial Index. What are the possible basic outcomes at the close of the trading day? The sample space for this experiment is as follows: S equals 1. The index is higher than at yesterday's close. 2. The index is not higher than at yesterday's close. One of these two outcomes must occur. They cannot occur simultaneously. Thus, these two outcomes constitute a sample space. An event, E, is any subset of basic outcomes from the sample space. An event occurs if the random experiment results in one of its constituent basic outcomes. The null event represents the absence of a basic outcome and is denoted by O. Let A and B be two events in the sample space S. Their intersection, denoted by A intersection B, is the set of all basic outcomes in S that belong to both A and B. Hence, the intersection A intersection B occurs if and only if both A and B occur. We use the term joint probability of A and B to denote the probability of the intersection of A and B. It is possible that the intersection of two events is the empty set. If the events A and B have no common basic outcomes, they are called mutually exclusive, and their intersection, A intersection B, is said to be the empty set, indicating that A intersection B has no members. Figure illustrates intersections using a Venn diagram. In part A of figure, the rectangle S represents the sample space, and the two closed figures represent the events A and B. Basic outcomes belonging to A are within the circle labeled A, and basic outcomes belonging to B are in the corresponding B circle. The intersection of A and B, A intersection B, is indicated by the shaded area where the figures intersect. We see that a basic outcome is in A intersection B if and only if it is in both A and B. In figure B, the figures do not intersect, indicating that events A and B are mutually exclusive. If the events A and B have no common basic outcomes, they are called mutually exclusive, and their intersection, A intersection B, is said to be the empty set, indicating that A intersection B has no members. Let A and B be two events in the sample space, S. Their union, denoted by AU-B, occurs if and only if either A or B, or both occur. The Venn diagram in figure shows the union, from which it is clear that a basic outcome will be in AU-B if and only if it is in either A or B, or both. If the union of several events covers the entire sample space, S, we say that these events are collectively exhaustive. Since every basic outcome is in S, it follows that every outcome of the random experiment will be in at least one of these events. We can see that the set of all basic outcomes contained in a sample space is both mutually exclusive and collectively exhaustive. We have already noted that these outcomes are such that one must occur, but no more than one can simultaneously occur. Let A be an event in the sample space, S. The set of basic outcomes of a random experiment belonging to S, but not to A, is called the complement of A and is denoted by AC. Clearly, events A and A are mutually exclusive, no basic outcome can belong to both, and collectively exhaustive, every basic outcome must belong to one or the other.